Okay, excuse me. Welcome to lecture. We'll get started here in just a sec. We're going to continue on, finish chapter 11, roll into chapter 12, and see how we do. Like usual, again, if you have any questions, feel free to type them in the box. Again, even if we've sort of moved on or anything like that, I'll be happy to go back and obviously answer your questions and stuff like that. All right, so we're talking about really alkenes, alkynes in this chapter. We talked about addition reactions that alkenes undergo. Remember, in an addition reaction, it's a very sort of simple formula. You take that double bond, and that double bond in the alkene is the only part of the molecule that changes. You simply turn that double bond into a single bond, and then you add in both things. So again, if you have that double bond and we do an addition reaction and we add, we'll just call it a 2A's or whatever. Again, everything looks the same, just that double bond. We turn that into a single bond like we talked about. Everything else on the molecule remains the same. Nothing else changes. And then we simply put one guy on one carbon and the other guy on the other carbon. Again, the purpose there is to make room for those guys coming in. So we had to break that double bond and make it a single bond. We talked about symmetrical addition, which is what this would be, where essentially you're adding two of the same. So in this case, we added an A to each carbon, which essentially means you can't really screw it up because, A goes to the left, A goes to the right, or you reverse it. It's the same end result. There's also some unsymmetrical addition reactions we talked about. A lot of those involve something like water, which is HOH. We think about it, HCl, HBr. It's really H and something else. And again, the same overall process occurs when you don't have an option. But when you do have an option, in the sense of when you look at that double bond, there might be one that has more hydrogens than the other. So for example, if we had this, those, and then maybe something like that. And when we look at this double bond, a little hard to see there on the top, but the right guy has two hydrogens to begin with. Left guy has one hydrogen to begin with. And in a situation where you have in that double bond that you're going to be breaking one carbon that has more hydrogen than another, the hydrogen part of what's coming in will always end up at the one that started with the most. So the hydrogen coming in ends up at the carbon with the most hydrogens to begin with. So if I were to sort of draw this here and I was adding the HBr, again, we would break that double bond, make it a single bond to allow room. We have our H's, we had our H here and our CH3. When we would add the H into this, again, it's going to end up at the one that started with the most, which in this case is this guy on the right. So he would get the hydrogen and the other guy would get the Br in this case, or the Cl, or the OH if it's in water and stuff like that. Any questions on that there? We also talked towards the end about benzene. Remember, benzene is a 6-member ring that has basically 3 double bonds in it. Can look like that. Can look like, very badly drawn, they'll throw me out organic soon. Look like that. And that's probably why I failed organic. There we go. Then like that. With the circle there in the middle, you oftentimes will see it, at least at our sort of level, sometimes that people won't draw the double bonds in, they'll just sort of draw the circle. And that's because, again, those double bonds could basically be moving around. We talked towards the end about how to name these guys. Essentially, if there's just one group attached, we just name the group and then put benzene at the end. If there's more than one group attached, we do number the groups to give alphabetically everybody sort of the smallest numbers. So if we look at these guys here, we have, again, this big part here, which is the main part of it, is our benzene. So it definitely wouldn't be the top guy because it has the double bonds. That's what the circle sort of implies. So it is definitely one of those two. And in this case, this is what, again, is what is referred to as being monosubstituted. There's only one group attached to it, which is a chlorine group, which is known as chloral. And again, because it's the only group attached, it's always assumed that that would then be carbon number 1. So you actually don't need to put the 1. So this would just be chlorobenzene. Looks like a winner, yeah, in terms of his name. Now here, when we do have two groups attached, again, the major part of it here is our benzene ring. So obviously all these have benzene. We also obviously have two methyl groups. So that's dimethyl, which again, they all essentially have. So what we want to think about this is sort of the numbering orientation. We want to always number. This can give our groups the smallest numbers. So if we go clockwise, we got a group at 1, 2, 3, 4, 5, and 6. And if we go counterclockwise, I'll just do it on the outside. 1, 2, 3, 4, 5, and 6. Obviously, this 5 goes to this carbon. So if we go clockwise, we end up with 1 and 3. We go counterclockwise, we end up with groups at 1 and 5. So again, it's always that smaller number. So this wouldn't be good. Obviously, it wouldn't be 1 and 4 either. So it would be what we got there, 1,3-dimethyl benzene would be the case here. Now, when we do have not necessarily benzene, or for example, but if we do have a cycloalkene, which you could have, by the way, so just so it's not confused, if I had this with just one double bond in it, this is not benzene. So again, benzene is a guy that has 3 double bonds in it. But it is based off of cyclohexane. Here, though, it has the double bond, so our cyclohexane becomes cyclohexene, yeah? So you would call that obviously cyclohexene, again, not a benzene ring. And for example, if we had the same ring, again, bad drawing there, and let's just say we had, a chlorine group here, and let's just say we had a chlorine group here, for example. And again, this is not benzene. It has just that one double bond. So the base of the name here is still going to be cyclohexene. Now, when we go to number, you could number like this way, 1 and 2, 3, 4, 5, and 6. Or you can number 1, 2, 3, 4, 5, and 6. There's actually a rule when you have sort of a ring that has one double bond in it. When you number, you do have to actually go through the double bond when you're numbering. So what that means is we technically would have to number this guy this way, because that is taking us, I'll just draw it really dark here, that's taking us through the double bond as we go in this direction. If we go in the other direction, we're not going through the double bond when we number it, so technically that is wrong. So although you could get to a smaller number by going left in this case, there is a rule where we have our double bond here that just made all solid. You do need to actually number and go through the double bond. And that would mean that this would then has to be 1,6-dichloral. I'll go above it since I'm running out of room there. Cyclohexene. So again, you don't want to confuse something like cyclohexene as a benzene ring because it does have one double bond. Again, the benzene ring will either be drawn like it is on the top right, or it will have that circle in it to indicate that it has basically those 3 double bonds. When you're dealing with benzene, it doesn't really matter which way you go because of the double bonds. What I mean in terms of the numbering is no matter which way you go, if you number that way, for example, or you number sort of the other way, you will always be going through technically a double bond. So you don't have to worry too much about numbering one way or the other with benzene. But technically, if you have something like this, which is a cycloalkene, you do have to number. And then when you're numbering, you got to make sure you go through the double bond when you're numbering. Any questions on that? Okay. So let's just kind of see what these would look like. We want to do the formulas here. And again, when we're doing these, just like normal, we want to work backwards. So if we go through these, the back part is benzene. So again, you can just draw your benzene ring. That's getting worse and worse as the day goes on. And again, you could put the little circle in it. You could do the 3 double bonds, whichever way you want to do it. Dichloral means that I got 2 chlorines at carbons number 1 and 2. So just like we talked about before, since you're drawing it, you can number whichever way you want. I'm going to go right to left, or I guess clockwise that would be, going this way. Again, you technically can go the other way if you like. So at carbon number 1, we should have a Cl. At carbon number 3, we should have a Cl, and that would be all she wrote in that case. Now, when we see 2-chloral toluene, remember that toluene is one of those historical sort of names that is associated with a benzene ring that has a methyl group at the end of it. So that this whole thing right here, again, not the greatestly drawn there. I'm just going to blame the computer. Is toluene here. And that pretty much will take care of this part. Since this was sort of the part of the main part, we'll call that carbon 1, which means carbon number 2 here. We would go with a Cl in this case. Any questions on those 2? Okay. So to finish up this chapter, we're going to talk about benzene and a reaction that benzene undergoes. And benzenes essentially will undergo a substitution reaction. So if you remember, we saw a substitution reaction with alkanes. In a substitution reaction, pretty much you're going to take one of those hydrogens, just like we did with the alkanes. It's going to go off. And just like we did with our alkanes, one of these chlorines is going to take its place. And when you do that, everything else exactly the same. Only difference is we took the hydrogen off and put the chlorine on, which is our substitution reaction. And just like what we had with our alkanes when we did the substitution reaction, the hydrogen that came off will hook up with the other halogen that is there and make something like hydrogen chloride in this case. Again, usually if you're asked to draw this reaction, it is like a monosubstituted. So remember, monosubstituted means we're essentially just going to take off one of the hydrogens and replace it with a halogen. As we'd also talked about, a lot of these reactions need some type of catalyst. So in this case, iron chloride is serving as a catalyst. Its sole function is just to speed it along, is not going to be introduced anywhere in terms of the reaction. You shouldn't try to put it on anything or anything like that. Any questions on the benzene reaction? So pretty much a very simple, and that's the way you want to think about these reactions. You want to extremely simplify it. All you have to remember is take a hydrogen off, put a halogen on. You're done. Draw everything exactly the same. As we talked about, you don't want to do any funky stuff like breaking rings open and adding all kinds of stuff. Again, most of the answers to these questions are actually found like right here on this side. Yeah. Again, if you don't overcomplicate it and try to do anything weird, remember there's only one part of the molecule that pretty much will change. All right. that is it for that chapter. So that should be chapter 11. Any questions on that? Yeah, so your question, I'll show it to you here. I think you can still see the screen. You could take any of those hydrogens. These hydrogens are what are referred to as being equivalent hydrogens. So they're all pretty much equal to each other. And usually if you're asked to do the monosubstituted product, you could choose any one you want. Again, they're essentially all equal to each other. You grab any one you like. So again, because technically just this ring, when we put the chlorine on over here, you can rotate it around and it would be in the same position. So you could grab any hydrogen you like. All right. Then we're going to go off to chapter 12. Did not like that. Let's try chapter 12 again, maybe. Try that chapter 12. Doesn't like that one better. Maybe. Nope, it does not. Let's see here. One of these chapter 12s has got to work. Let's see. All right, hopefully that one worked. Sorry about that. Hang on here. All right. Okay. So chapter 12, we're going to talk about alcohols. We're going to talk about ethers. We're going to talk about aldehydes, ketones, and a whole bunch of guys. So just to sort of talk about sort of the functional groups of each of these, and we're going to talk about each of them specifically in just a second. Let's see if that's better. So let's start with alcohols. So alcohols are an organic group, and the functional group of an alcohol is that OH group. So when we see that OH group, that is our functional group. Remember, the functional group of an organic compound is the part of the molecule that is what makes it a certain type of organic molecule. So alcohols have a functional group of the OH group. Ethers is another group of organic molecules. They have the functional group of a carbon, oxygen, carbon run. So they got this carbon, oxygen, carbon run, which you can see right here, carbon, oxygen, and carbon, which would be the functional group of an ether. We kind of already talked about alkyl halides. Alkyl halides are pretty much what happens when you add a halogen to an alkane. So that was that halogenation reaction we talked with alkanes, where we take off a hydrogen and put a halogen on there. Thiols is a sulfur-containing group. So the functional group for a thiol is that sulfur-containing group. So usually SH is the functional group that we think about when we think about thiols. Obviously, it has sulfur in it. Doesn't smell too good. And then we get to a couple other really big groups, which are aldehydes and ketones. Aldehydes, as you'll see, and again, we'll go through each of these separately as well through this chapter. Aldehydes functional group is the carbon oxygen double bond with the hydrogen is the functional group. Remember that when you have the carbon oxygen double bond, That is what they call a carbonyl, or a carbonyl carbon is sometimes referred to. A ketone has a functional group where we have basically 3 carbon run. So you need like a 3 carbon run in it, and you have a carbon oxygen double bond in the middle of that 3 carbon run. So if we look at these couple of examples here, on the right here, this is the functional part of our aldehyde. Carbon oxygen double bond with the hydrogen, and here is that 3 carbon run. 1, 2, and 3 carbons in a row with the carbon oxygen double bond always in that kind of middle carbon of the 3 carbons in a row. So again, that carbonyl carbon there in the middle of a 3 carbon run that has a carbon oxygen double bond is going to be a ketone. So remember that you do need to know the functional groups. You need to be able to identify what type of organic molecule it is based off of its functional group. And it's also really important, as we'll see as we go through this as well, it's going to be really important in terms of how we name these things. So you need to be able to identify the functional groups as that is the functional group for an aldehyde. The bottom there is the functional group for a ketone. And again, that's going to help you focus in on sort of how to correctly name these guys. So let us start with alcohols and sort of the properties that we find with alcohols. Again, whenever you see this right here, that is going to be an organic group, which is an alcohol. And alcohols can be classified just like carbons as primary, secondary, or tertiary. So if you remember, the way we classify carbons is a carbon that's attached to one other carbon. So this carbon would be primary. A carbon that's attached to 2 other carbons, like this guy here, would be a secondary. And then obviously a carbon that's attached to 3 other carbons would be a tertiary. And alcohols work the same way. The difference is what carbon you're looking at is a specific one. You're actually looking for the carbon that has the OH group attached. So you want to find the carbon that has the OH group attached, and then you want to figure out how many carbons are attached to it. So first, this is the carbon that has the OH group. Now this carbon is attached to just one other carbon, and that would make this a primary alcohol. So we want to look at the carbon that has the OH group. We want to figure out how many other carbons are attached directly to it, and that will tell you it's primary. If we look at a couple more examples of, say, secondary or tertiary, I found an error. That ain't good. Bad. Give me 1 second. Apparently, it just crashed. Give me 1 second to reboot that up there. Should really have some type of music, so short interlude or something like that. There we go. We're going so well there. All right. Sure, let's try that one. Let's see if that one opens. Okay, let's do that. Okay, and we were somewhere. Where were we? Right there. Yep. Okay. Let's give that a go again. Maybe it'll be happier. Let's try that. There we go. Let's do that. Back we come. Hopefully. Okay. So back to this again, secondary and tertiary here. Again, the important carbon is going to be the one that has the OH group attached to it. So in this case, this would be the carbon we're looking at. And again, added directly to it or attached directly to it is one carbon there and one carbon there, which is two carbons. And this would be a secondary alcohol because of that. And lastly, if we come down to our bottom guy here, again, the carbon here in the middle is the important one. It has the OH group attached to it. Directly attached to that carbon with the OH group is one carbon there, two carbons there, and lucky number 3 carbons there, which will give us the tertiary alcohol. So we oftentimes will classify alcohols as primary, secondary, or tertiary. And again, you want to do it pretty much the same way as you do carbons. The important carbon to look at, though, is the one that is attached directly to the OH group. And then you need to figure out how many are attached to it in terms of carbons. Now, alcohols have that OH group. And if you remember, that OH group is a polar group. The oxygen is more negative, hydrogen is more positive. That gives alcohols the ability to do that intermolecular force like hydrogen bonding. So our alcohols here can do some hydrogen bonding. And if you remember when we talked about intermolecular forces, hydrogen bonding is a very strong intermolecular force. It's the strongest out of those 3 that we talked about. Hydrogen bonding is the strongest, followed by dipole, and dispersion forces are the weakest. So this means a couple of things about alcohols. Smaller alcohols have the ability, like I drew up there, to interact with water because they can hydrogen bond with water, which means the smaller alcohols, like 6 carbons or less, are typically soluble in water because they do have that ability to hydrogen bond. In addition, because they can hydrogen bond, the bond between 2 alcohols is going to be relatively stronger. And because it's going to be relatively stronger, that means that we typically see high boiling points. So very much butchered boiling points. So we see very high boiling points with alcohols because of the ability to hydrogen bond. It is definitely a lot stronger than an alkane, or an alkyne. Because remember, alkanes, alkenes, and alkynes, they're all carbons and hydrogens, which means that they could use not dipole, and not hydrogen bonding. They use the weakest out of all of those. They use dispersion forces. And that means those guys typically have very low boiling points. And that's what we see here in comparison of our alcohol and our alkane. Alkane using dispersion forces, very low boiling points and melting points, as opposed to here our alcohol, which has the ability to hydrogen bond. You can see a significant difference in the boiling point, obviously, because of that ability to hydrogen bond. So in terms of boiling points at this point, in terms of order, the alcohols are at the top in terms of boiling points, have the highest are alkanes, alkenes, and alkenes, and alkynes would be lower boiling points. And remember, as we talked about with the alkanes, alkenes, and alkynes, even though they're all using dispersion forces, the boiling point will increase with size. So the bigger the size, the higher the boiling point for something that can only use dispersion forces. And as I mentioned, alcohols that are about 6 carbons or less are usually fairly soluble in water, and usually are soluble also in organic compounds. But, the point of their solubility is really tied to this bond here in the alcohols. So if you keep building a lot more carbons and hydrogens, I'm not going to draw the hydrogens, but there'd be hydrogens on all these. You know, I ran out of the screen there. What you're doing, the solubility definitely will start to decrease a lot because you pretty much have two sides to this alcohol. This side over here, which again, I didn't draw the hydrogens, is pretty much all carbons and hydrogens and non-polar. And really the only polar part of this molecule would be over here where we have that group. So when you get to really a lot of carbons, like, more than 6 usually, the non-polar side pretty much gets in the way. And it doesn't allow this guy to interact really well with water because it's a lot bigger. The non-polar side is much bigger than the polar side, and it's not very soluble. But usually if you're up to about 6 carbons or so, you're usually okay in terms of solubility with water. So let's talk about how we name them. So alcohols, again, it does end in OL, right? And that's pretty much what we do. We pretty much drop the last part of the name and replace it with OL. Now, if you remember when we were naming our double bonds, our triple bonds, when we would name them, we would oftentimes have to give the location of the double bond or triple bond. And the same thing sort of happens with alcohols, especially when you start getting into a situation where you have more than one option where the OH group would be. You do need to give the number of the OH group. And just like the double bonds and the triple bonds, when you go to number the longest continuous carbon chain, two things has to happen. The longest continuous carbon chain does need to contain the OH group in it. And secondly, when you number the longest continuous carbon chain, it is the OH group that gets the priority in terms of numbering. So you want to number whichever way is going to give the OH group the smaller number. Now, some you don't really necessarily need any type of numbering. So for example, if I have this here, let's draw it out. Or if I have this guy here, this is one carbon, and alcohols, like everything else, will come back to those alkanes. So one carbon is based off of CH4, which is methane. Since it has this OH group, methane becomes methanol, OL. Because there's only one carbon in this case, you don't need to give the location of where that OH group is at because it's only going to be at carbon number 1. We look at the next guy. That is 1 carbon, 2 carbons, also based off of 2 carbons, which is ethane. Has the OH group. So our ethane becomes our ethanol. Again, here you do not need to give the location of where the OH group is because if you number this would be carbon number 1 and carbon number 2. And if you put the OH group on the other side, so I'll just kind of draw it like this. So even though these two pictures look different, if you were to number it, because this would get the priority, this would be carbon 1 and carbon 2. So no matter which way you would go, the OH group is at carbon number 1, and thus we don't need a number for it. But if you had something like this, or if you had something like this, When we look at this, and just like we name everything else, we're looking for the longest continuous carbon chain that contains the OH group. And if we go on the guy on the left, this is 1, 2, and 3 that contains the OH group. 3 is based off of propane. Again, it becomes propanol, OL. The location of the OH group, which would get the priority, we would then want to number right to left, 1, 2, and 3. This would be what is known as 1-propanol, the 1 for the location of where the OH group is at. Now, if we do the same thing to the guy on the right, we got 1, 2, and 3 that contains the OH group. Also going to be propanol. Now, when we number it, we could go right to left, which would be 1, 2, and 3. We could actually go the other way too, 1, 2, and 3. No matter which way you go, the OH group is at carbon number 2. This would be known as 2-propanol. And in this case, there could be a difference as to where you find the OH group. In the case on the left, it's at carbon number 1. In the case on the right, it's at carbon number 2. So in this case, starting about 3 carbons or more, that is an alcohol, you do have to give the location of the OH group. Again, when you number, the OH group gets the priority. So it should always have the lower number, regardless of what other groups are attached. The OH group should get the lowest number. Much like what we did with the double bond and triple bond, once you lock it in terms of which way you're numbering, you got to keep that way of numbering for everybody else that's attached. 2-propanol, also known as isopropyl alcohol, also known as rubbing alcohol. So a lot of different names used for the same thing, which is very common in organic chemistry. Any questions on that there? So if we look at this guy here, again, we could kind of go through our steps. We want to find the longest continuous chain that has the OH group in it. So if we count, going left to right, 1, 2, 3, 4, 5 carbons. If we started up on top, 1, 2, 3, 4 carbons, start at the bottom, 1, 2, 3, 4 carbons. So 5 carbons looks like the longest continuous carbon chain. Again, 5 carbons is going to be based off of pentane. Because we see the OH group here, we know it's now going to be known as pentanol, OL. Now, when we number this chain, remember we want to number whichever way is going to give our OH group the smaller number. So you could hopefully be able to see that if we go left to right, we will get a larger number than if we go right to left. So in this particular case, we would want to go right to left. So that'd be carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. So this now becomes 1-pentanol, the 1 for the location of the double of the OH group. We also have 2 other groups attached. We have a methyl group here, and we have a methyl group here. That's going to give us a dimethyl. And number-wise, because we locked in going right to left, we have to keep those numberings for the groups. And that means that carbon number 3 and carbon number 3, you have 2 methyl groups. So that would be 3,3-dimethyl pentanol. Any questions on how we got that? 3,3-dimethyl 1-pentanol. I'm sorry, I missed the one there when I said it. I have it written there. So 3,3-dimethyl 1-pentanol. Any questions on that name? Now scroll this through is pretty much what we just did there. Hopefully they end up with the same name, which it looks like they did, so that's good. So remember that the name is all about location, right? So even if the two groups are on the same carbon, you do have to give the number twice, even if they're the same group. Again, each of the threes do go with one methyl. So say the first three is the methyl on top, the second three is the methyl on the bottom. So you do have to give both threes for sure down here because of that. Now, when we do have alcohols that can be in a ring structure, we name it just like everything else. So in a ring structure, this is a alkane that is 6 carbons, and that would be based off of cyclohexane. We see the OH group, which turns our cyclohexane into cyclohexanol to indicate that it's an alcohol. Now, in a ring situation, you don't actually have to give the location of that OH group. It is always assumed to be carbon number 1. So you don't have to put it into the name in a ring structure when you have an OH group. But the important part is it then becomes carbon number 1 wherever it is located. And in this case, we do have 2 ways to get to that methyl group. We could go counterclockwise, which gives us 3. We could go clockwise, which would give us, if I knew how to count, that would be 3. That would be 4. I guess 5 would come after that. That's good. So obviously that would give us a larger number, even with my bad counting there. And we would want to give it the smaller number. So again, we would want a number in this direction here. And that again is how we get to 3-methyl for the methyl group that's attached to the ring. This OH group is taken care of right here when we say cyclohexanol. And again, because it's a ring structure, you don't have to give the location of it. Any questions on that? All right, so you got a few here. Why don't you take a couple minutes here and why don't you name all 4 of those, it looks like. See what you come up with. Okay, let's see how we're doing. So, and remember that we always want to go for the longest carbon chain. Remember that the longest carbon chain does need to contain the OH group in this case. So if we go on the top one here, right across 1, 2, 3, 4 carbons, and that OH group, or you can even start at the top and go 1, 2, 3, 4 carbons. So just like anything else, sometimes it's best to take the straightest, which would be like here, right? Since it has the OH group, I guess I should kind of sandwich that in with it. So that is 4 carbons. 4 carbons based off of butane, has the OH group, so it becomes butanol. We want to give the OH group the smallest numbers. So in this case, we would want to go right to left, because going right to left, that's going to give our OH group carbon number 2. If we went left to right, we would end up with carbon number 3 for the OH group. And again, it is always the OH group in this case that gets the priority. So the 2-butanol means that we have an OH group at carbon number 2. Because we then have locked into place numbering in this direction, that means that our methyl group would have to be at carbon number 3. So this would be 3-methyl 2-butanol. Any questions on that particular one? By the way, this alcohol here, would it be a primary, secondary, or tertiary alcohol? So I want you to take a second and think about that. And hopefully, if when you're looking at it, again, the key is to look at the carbon that is attached to the OH group. So this carbon then has 1 carbon attached directly to it. It has 2 carbons attached directly to it. This would be a secondary alcohol because of that. Yeah, very good. Secondary. Perfect. Any questions on that there? All right, so let's take a look over here. Again, we have a 6-member ring based off of cyclohexane, has our OH group there. Going to become then cyclohexanol. Not needed is the numbering for that OH group in a ring, but it does become carbon number 1. And again, in this case, we would want to go counterclockwise, as that will give our group there the smaller number. And this should be 3-methyl cyclohexanol. Now, when we look at this one, this is a carbon here, which then would be attached to 1 carbon there and 1 carbon there. This also would be a secondary alcohol because of that. Any questions on that there? Coming down over here, longest carbon chain with the OH group is 3. So 3 based off of propane becomes propanol. OH group, no matter which way you go, is going to end up at carbon number 2. So that is 2-propanol. And then we have a methyl group also at carbon number 2. This is 2-methyl 2-propanol. Question on that name. This guy would be a primary, secondary, tertiary. What do you think? It would be a tertiary. It would be, again, when we look at this carbon here, which is directly attached to the OH group, it is also directly attached to 1 carbon there, 2 carbons there, and 3 carbons there. So it would be a tertiary alcohol. Very good. And lastly here, this is one that I think we named earlier. We have 3 carbons in a row. So this is going to be our propanol. And it's at carbon number 1, 2, and 3. So that's going to be 2-propanol, which again is sometimes called still isopropyl alcohol and basically rubbing alcohol. And 2-propanol, as you could perhaps guess from the name, actually, is attached to 1 carbon there, 2 carbons there, is also a secondary alcohol as well. Any questions on how to name or how to classify them as primary, secondary, or tertiary? Okay. So here's a couple more. Let's just look at perhaps, let's just look at the bottom 2, I think. So again, if we look at it, longest carbon chain, 1, 2, 3, 4, 5. So again, that's going to be pentanol. OH group, we would want a number right to left, as it will give that OH group the smaller number. So that's going to be 2-pentanol. And again, the CH3 is also on the 2. So this would be 2-methyl 2-pentanol. This is also a tertiary alcohol as well. It is attached to 1, 2, and 3 carbons in this particular case. This guy here is a condensed formula for something that looks like this, usually, like a square with an OH on it. 4 carbons in a ring structure is based off of cyclobutane, becomes cyclobutanol. No need for a number because this is assumed to be carbon number 1, and there's no other group attached. And again, this is a secondary alcohol because this carbon's attached to 1 carbon and 2 carbons. This alcohol, which is ethanol, is a primary alcohol as it is attached to 1 carbon. And this guy over here, which is our 1, 2, 3, 4, our 2-butanol, is a 1 carbon, 2 carbons, a secondary alcohol as well. Any questions on naming or any of that type of stuff? Okay, let's talk about some reactions that alcohols undergo. The first type of reaction is what is known as a dehydration reaction, and that is really the opposite of a hydration reaction. So a hydration reaction we talked about with our alkenes, that's the unsymmetrical addition. Remember, that's how we get to there, right? That addition reaction that we talked about, where our double bond becomes a single bond, H goes to 1, OH goes to the other. Again, that is a hydration reaction, which is what we talked about in the previous chapter. The opposite of that is a dehydration reaction. And just like it goes on, so just like when we put the hydrogen and OH on, these go on to separate carbons. When it comes off, we take an H off of 1 carbon, we take an OH off of the other, and when we break the bond to put it on, we need to put the bond back in. So in a dehydration reaction, you take off a hydrogen from 1 carbon, OH from the other carbon, and then you put a double bond back in between the carbons that you did that to. Usually requires sulfuric acid as a catalyst. Again, not going to really participate per se. Nothing in the sulfate or anything like that gets involved. This is what is sometimes referred to as an elimination reaction. We're basically taking away something. Remember, the addition reaction is when we put it on. The elimination reaction would be the opposite when we take it off. See if we have another example of that. Yeah, so here again is another example, a couple examples when you see an alcohol and you see something like sulfuric acid, you may just see generically H plus. You may even see like a delta symbol that means heat with it. That will tell you that it's pretty much going to go through this dehydration reaction. So again, we're going to take off a hydrogen from one, an OH from the other, and in between them, where we took it off, that is where we add that double bond in to there. Again, nothing else changes. H, 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 and H. And then obviously when we take off the water, we would produce water in that case. Same thing here. We're going to take off an H from one, OH from another, and again, going to put the double bond in between the two carbons where we took off those two groups. So dehydration is a pretty simple sort of one. It is the exact opposite of putting on the water. We're going to take it off. Now, if we had something like, let's see here, try to do it right here. Let's do that. Actually, that's not what I want to draw. Let me try this again here. Good thing they made erasers even online. All right. Let's see. What I'm trying to do is, I think. Okay, so if we were going to take this alcohol here and put it through a sort of dehydration reaction like we're doing here, we're going to take off a hydrogen. We're going to take off an OH group. So when we take off the OH group right here, now we need to take off a hydrogen. And in this case, we actually have a choice. We could take off a hydrogen from this carbon. We could also take off a hydrogen from that carbon. And the difference would be if we took the hydrogen off the first guy, we would end up with something that looks like this. Double bond would end up between those two. And we would end up with something like this. And that would be, again, taking off, say, the hydrogen over here on the left. Now, if I did the opposite and took the hydrogen over here on the right off, we would end up with something, again, nothing changes, so everything looks the same. We're going to take off that OH. We're going to take off the hydrogen to the right, and that's where our double bond is going to go. And we end up with an option of basically two products that we could get. We could get the guy on the top there, we get the guy on the bottom. And if you remember, when you have an option in terms of adding the water, so if you remember when you add the H and the OH, the H always goes to the carbon that started with the most hydrogens. And when you do the opposite, you actually remove it from the hydrogen from the carbon with the least. So when you do the dehydration reaction, you technically would most likely end up with this hydrogen over here being removed and actually giving you this as your sort of major product. So if you do have an option in terms of the dehydration reaction, it's sort of opposite of how it goes on. So we put the hydrogen on the one with the most. When we take off the water, we take the hydrogen from the one with the least when you do have the option. So there is sort of that rule that is very similar to how it goes on, but it's sort of the opposite when you take it off. So if you don't have an option in terms of these examples here, if you went to the right, it's the same number of hydrogens as you went to the left. So technically you could have double bonded over here as well. It's the same guy as you get over here. Any questions on dehydration? So you want to take off a hydrogen from one carbon and an OH group from another. Now let's talk about reactions that alcohols do, and these are what are referred to as oxidation reactions. And oxidation reactions is what that means right there. It's going through an oxidation reaction. And if you remember, oxidation has a few definitions, but essentially for organic, it means that you gain oxygen as you go from reactants to products, or you lose hydrogen, which is like H2, as you go from reactants to products. While reduction, in the sense of sort of organic chemistry, is the opposite. You will lose oxygen as you go from reactants to products, or you would gain hydrogen, or H2, as you go from reactants to products. So when we take an alcohol, what's going to happen when we do an oxidation reaction with an alcohol, the definition that we're going to usually see with alcohols is this definition right here. We're going to lose hydrogen, and hydrogen is basically H2. And the hydrogen will come off, one hydrogen always from the OH group. The other hydrogen will come off from the carbon that's attached to the OH group. Now remember, when we lose H2, or two hydrogens, we do need to replace it with a double bond. And you end up getting this double bond that happens between the carbon and the oxygen that lost the two hydrogens. So when we look at a oxidation reaction, again, it's replaced by taking a carbon hydrogen bond and putting basically a carbon oxygen bond in between it, and this is things becoming oxidized. Again, here we're gaining oxygen, we're losing hydrogen, we're gaining oxygen, and again we're losing hydrogen. So these are all sort of oxidation reactions that are happening. Again, as you go from this guy to this guy, you gain oxygen. As you go from this guy to this guy, you lose hydrogen. As you go from this guy to this guy, you gained oxygen. And lastly, as you go from that guy to here, you lost hydrogen. And again, those are all definitions of oxidation. Remember that oxidation also goes with reduction, which technically means if you head in the opposite direction, these are all reduction reactions, as they always go together. Reduction is sometimes abbreviated like this in organic chemistry. So sometimes that's used to indicate a reduction reaction heading in the opposite direction. So let's talk about what happens with a primary alcohol. When we take a primary alcohol and you put it through an oxidation reaction, we lose our H2. And those are the wrong H2s that I circled. So let me get that up. Just saw a hydrogen and went for it. All right. Sorry. H on the carbon and H on the O there. I'm sorry. So these two come off. And again, where those come off, we're just going to simply insert the double bond there. So if you take a primary alcohol and you oxidize it, you will get this guy right here, which if we see this functional group, you get what is known as an aldehyde, which has that carbon-oxygen double bond with the H as the functional group. And as we'll talk about as well in a later chapter as well, if you then oxidize an aldehyde, it will go to this organic group, which is a carboxylic acid. And it has the functional group of carbon-oxygen double bond with an OH. But when you're talking about alcohols, it's simply alcohols, primary alcohol, oxidized to an aldehyde is usually where you would probably stop unless you continue the oxidation. And nothing changes in this molecule other than you take 2 hydrogens off and you basically put that double bond in its place. Now, if we go to a secondary alcohol, the same thing is going to happen. The H from the OH group and the H from the carbon will come off basically and make H2. And what's going to happen is if we take a secondary alcohol and you oxidize it, you will get this guy, which is a 3 carbon in a row with the carbon-oxygen double bond. That is what is known as a ketone. That 3 carbons in a row with your double bond in the middle. So if you take a primary alcohol and oxidize it, you will get a aldehyde. If you take a secondary alcohol and you oxidize it, you will get a ketone. And by the way, if you go backwards, this would be the reduction, right? So if you reduce an aldehyde, you get an alcohol. And if you do the opposite, going in the opposite direction here, the reduction, you would go from a ketone to an alcohol. So again, they're opposites of each other. Oxidation and reduction happen together, or they happen sort of at the same time with the same stuff. But for purposes of alcohols, secondary alcohol gets you a ketone if you go through an oxidation. Now, if we look at our tertiary alcohol, we're going to take the H from the OH, and we need that second H, but there is no second H. Remember that these R groups are carbon, so essentially this is what you got going there. So because these are attached to carbons, this guy, he is missing that second H that is needed for an oxidation reaction to occur. So we actually get no reaction. So if you take a tertiary alcohol and you try to go through an oxidation, you get nothing, no reaction. Again, because a tertiary alcohol is missing that crucial second hydrogen that is needed for the oxidation to occur. Questions on that? So for example, again, none of these are change all that much. Let me just go find somewhere that's kind of clean that can be right on. Too much stuff. All right, let's go here. Actually, we'll go on top. All right, so let's say we had these guys. So let's say we had all right. So why don't you draw the product of this oxidation and also draw the product of this oxidation. And draw the product of this oxidation. And lastly, why don't you draw the product of this guy's oxidation. All right, so why don't you take a few minutes and draw the products of each of these oxidations. and see what you come up with. Okay, so let's take a look. Just wanted to kind of get something to write on here. All right, let's see here. All right, so all these are alcohols, and obviously when you see that little O symbol, it means they're all going to go through oxidation. So again, what you want to think about in terms of the oxidation is we're basically going to remove two hydrogens, one from the OH group and one from the carbon that's attached to the OH group. And remember, when we remove those two hydrogens, we're going to just slap a double bond between the carbon and the oxygen. So I'm just going to redraw the first one here. I'm just going to draw it out so we can kind of see all the hydrogens and everything. So if we draw out that first guy, it will look something like this. And I'm just going to draw the OH group on top. You could leave it where it was. It doesn't really matter. So when we go through this oxidation, what we're going to do is basically just slap out two hydrogens. Again, the 2 hydrogens will always be taken from a certain spot. The one spot for sure is always attached to the O. And the other one, for example, is attached to the carbon. It doesn't matter which one you grab. When you do that, those 2 guys are going to make H2, which is basically your definition of oxidation. And everything here on the left-hand side will be exactly the same. So you should just draw it exactly the way it looks. Again, you shouldn't do anything funny. So I essentially drew it exactly the way it was. The only thing that I didn't draw were the 2 hydrogens I took out. And now in place of those 2 hydrogens, between always the carbon and the oxygen in this case, we're going to make that a double bond. And if you want to finish it, you can put the dots there if you like. Sometimes people don't do that so much. And what we get again, this alcohol is a primary alcohol. Goes to a aldehyde, right? Which is that functional group of carbon, oxygen, hydrogen. As we talked about here, this is ethanol. And believe it or not, an aldehyde ends in Al. This is ethanol, Al, which is how you would name the aldehyde. Question on that first one there. Let's take a look at the second one. Again, here I'm going to kind of redraw out so you can see everything. And again, I'm just going to put the OH on top. You could leave it on the bottom. It's fine. I'm just going to do it for this purpose. So again, when this goes through an oxidation, just like the top one, we want to think about removing the 2 H's. Again, 1 H from the OH group right here. Second H from the carbon that it came from. Everything else is exactly the same. So you should just copy what you got there on the left, taking out those 2 hydrogens. And now once we take out the 2 hydrogens, that is where we put our double bond into it. And this guy is a 1,2 secondary alcohol. That oxidizes into a ketone, which is a 1, 2, and 3 carbon run, and also based off of 4 carbons, which is based off of butane. ONE is our ketone that becomes 2-butanone, ONE. 2 for the location of where this guy's at. We'll talk about naming that a little bit later on in this chapter as well. Any questions on that one there? Now going to our top, we have our OH. Remember that this is a carbon right here that has 1 hydrogen, and that is exactly what we're going to take off, an H there and the H that's attached there. This square still remains a square, doesn't open up. And the double bond would be between that carbon and that oxygen that's at the end. And it would look something like that. Again, this alcohol, as we talked about previously, is a secondary alcohol, which also ends up as a ketone, right? Again, 1 carbon, 2 carbons, 3 carbon run, carbon oxygen double bond makes it a ketone. Now the last one here, this is a 1, 2, and 3 tertiary alcohol. So we're going to take the H off of here. And as we talked about just a minute ago, we have no H here, which means we're actually going to get no reaction for this guy because he is a tertiary alcohol and he does not have that second hydrogen that is necessary for it to go through a oxidation reaction. Any questions on how to draw the products of these oxidation reactions? So primary alcohol goes to an aldehyde. Secondary alcohol goes to a ketone. Tertiary alcohol will not oxidize because it's missing that second hydrogen. All the oxidation reactions here for these alcohols are the same. Hydrogen off of the OH group, hydrogen off of the carbon attached to the oxygen, put a double bond between the carbon and the oxygen, draw everything else exactly the same, and you will be in business. Any questions on any of that stuff there? Okay, so we will stop here for lecture today. What I'm going to do, I think, is what I said last time. So we're going to take a little bit of a break here, maybe about 15-minute break, and then we'll come back and I will lecture for a little bit during discussion just to try to get us on track and stuff like that. A reminder, as we talked about last time, and I will post it. I haven't got a chance to do so yet, but I will post on Canvas. The exam will be moved to, I want to say the 11th. Does that sound right? No, maybe. It will be moved to the 11th of May. And then we'll have the final, I think the following week, I think is when the final will be. Any questions on any of that stuff? Okay, so we're going to take a break. Like I said, take about a 15-minute break. We'll come back. We'll lecture maybe for just a little bit. And if you can come back for discussion, please do. If you can't, then obviously I will post it up online with this one, and you can watch it, the recording of it if you can't make it and stuff like that. But I am going to start the discussion in the separate sort of Zoom. So come through that one as well. That way the recordings will be kept separate, and will start with a kind of a fresh recording for discussion. All right, so we'll take about a 15-minute break. And again, you're welcome to come back and listen. Otherwise, I'll just talk to myself. And I'll post it up online. Hopefully we'll get a good portion of the rest of this chapter kind of get in place. All right, I'll see you in a bit.